Welcome to the 24 Hours of Past SQL Server 2014. We're excited you could join us today for Jamie Redding's session on SQL Server 2014 In-Memory OLTP overview. This 24 Hours of Past event consists of 12 consecutive live broadcasts followed by an on-demand replay. To access any on-demand sessions, please refer to 24hoursofpast.com for all session links. My name is Ben DeBoe, and I'm a partner at SQL, which focuses on mission-critical systems. And I have a few quick introduction slides before I hand the reins over to Jamie Redding. He'll speak for about 40 to 45 minutes, and then we'll move on to some Q&A where you can ask them any questions that you may have. If you're having any issues, just raise your hand using the hand icon on the right side of your screen and someone will assist you. To maximize your screen, use the Zoom button located on the top of the presentation window. Feel free to enter the questions in the Q&A field at any time. Questions pane is located on the right side of your screen. Once we get to the Q&A portion of the session, I'll read off your questions to the speaker. Since all attendees are muted, you'll need to submit your questions by typing in the Q&A field. Note that there will be a short evaluation at the end of the session, and your feedback is important to us, so please make sure you take a moment to complete it. It'll show up on your screen at the end of the session. Also, we'd like to thank Microsoft for being our event partner, and Microsoft is one of our global sponsors. The staging of 24 Hours of Past would not be possible without their support and dedication, and they are the reason this event is available free of charge. Next, I'd like to bring your attention to the upcoming PAST Summit. Taking place in Seattle, Washington this November 4th through 7th, PAST Summit 2014 will feature over 200 sessions with world-class SQL Server experts. Planned and presented by the SQL Server community for the SQL Server community, PAST Summit is single-handedly the largest gathering of SQL Server and BI professionals. With over 5,000 attendees from all over the world, PAST Summit is also a great place to network and meet face-to-face with experts, peers, and MVPs. More importantly, PAST Summit delivers on providing you the answers to your SQL Server issues along with knowledge, strategies, and skills you may need to stay ahead of the curve. Contact your local chapter for a discount code to save $150 off, and optimize your savings by registering before Friday, June 27th. To find out more about PAST Summit, please visit www.pastsummit.com. And now, please allow me to present the speaker of the hour, Jamie Redding. He's a senior program manager at Microsoft, and he's been working with Microsoft and the SQL Server team for over 16 years. His primary focus is TPC benchmarking and performance, and he has also worked with IBM and Compact. To you, Jamie.
All right, thank you, Ben. So we're going to cover today the In-Memory OLTP functionality of SQL Server 2014. So it'll be an overview session, so we'll kind of hit a bunch of different areas. There'll be more detailed sessions, I guess, later in the day today. So when we started doing 2014, we had a bunch of investment areas to look at. In-memory stuff, the first block there, we had some changes to the always-on system for high availability and backup. Also, a lot of things added to the cloud. So to support SQL and Windows Azure, you can do backup to the cloud, you can do HA to the cloud, as well as deploy your databases to the Azure system. We also spent a lot of time working with the Windows team to make sure that we work better with Windows than we did in the past. So there's a lot of investments going on there, but the primary we're going to focus on today is going to be the OLTP, or the in-memory part of it. So in-memory OLTP, so the numbers there, 5-10x performance gains for integrations for SQL Server. It's a range. Your mileage may vary. These are for transactional workloads, high-speed transactional workloads, primarily short transactions, concurrent data entry, processing retrieval, so very high throughput environments are really used for the in-memory OLTP system. We also added in-memory DW, or expanded upon that from the previous product. Again, numbers, 5-10x performance gains, high-end data compression, updatable and clustered. Basically, they're just designed for decision support workloads, So as you start doing more decision support workloads, you need to have larger scans and aggregates of data out there. So now with the new cluster columns or indexes, you can get very high-speed access back to that data for analytical queries, and you can also save space because we do aggressive compression on that data. The final piece for in-memory is an extension to our buffer pool. So traditional SQL Server has a buffer pool where we keep all our working set data. We also add the ability to add an SSD extension to that one. So several vendors have, use the word appliance, that lets you put a high-speed buffer pool out there. attached to the SQL Server. It's transparent to your end users, transparent to everything in the system. But again, disk-based transactional, not in memory, and for a large working set. So as you fill up your normal SQL Server buffer cache, it spills over to the high-speed SSD buffer cache without any kind of user intervention. Very powerful way to expand a system and provide high-speed access back to the data. So we're going to cover a few things in the presentation the rest we go through versus motivating trends. So why do we do this? And then we'll talk about the architecture, integration, performance, and then finally reviews and references of it. So In-Memory OLTP, you may have heard about this when it first announced. It was codenamed Hekaton, was thrown around quite a bit. We still call it that internally because it just makes more sense, easier to say than In-Memory OLTP. So the customer demand we were seeing was very high for throughput and high latency. So you had environments that were architecture. We need to meet those demands. So with In-Memory OLTP, we've got a high-performance system optimized for transactional throughput, no locking, no latching in that system. We have an OLTP engine that's memory optimized, so it understands what happens in the environment. And it's all in the same package. So you buy SQL Server 2014, you get traditional disk-based tables, as well as your In-Memory OLTP system, as well as your cluster column store for DW queries, other packages all in one single package. We also took a shift here and said, let's look what the new hardware is, where it is today and where it's going, and try to architect that for the modern hardware. So you'll notice there's no more support for x86 systems, all x64, higher memory support. That's all happening in the new product. So hardware trends. So where is it going? Where was it going? Where is it come from and where is it going? So the top band there is the green band. That basically is the transistors in the processor. So Intel's done a great job of following Moore's law. We see the nice curve there. And clock speeds have kind of leveled off. So Moore's law is still holding. We see that every day from Intel coming out. But the CPU clock rate stalling. So you're getting more processors, more cores, but the clock rate's not changing on us. And that's because things would melt. We're getting a lot more power coming to these systems, a lot more heat generated, so there's a lot of work to get the heat pumped off those systems, and that causes, again, problems there. So a new CPU, though it's more cores very fast, won't run a short transaction faster. It may not hold it for the DW cores. You're doing large aggregates where you can take advantage of that one, but short transactions don't run any faster in that environment. But you also see that RAM continues to drop. So the prices of RAM and the amount you can put on a single system is on a downward trend. That's a good thing for in-memory systems. So taking that, we built Hekaton or In-Memory OLTP. So there's several pillars that we use to build this thing with. So the first one is for high performance data operations. So we see, again, memory price coming down, memory RAM available to come down lower. So you took an architecture called main memory optimize. We took the memory, optimized it for in-memory data, so not for disk space anymore. We have hash indexes and range indexes is only in memory as well, so not persistent on disk. There's no buffer pool, there's no B trees, and it's a stream-based storage system. So it's designed to be very, very fast, high performance, and very transactional in nature. So as you have clock rates, we saw in the last chart, were kind of slowing down. We need to figure out a way to get around that. So one way was to take the SQL code used today, the same SQL code, and compile it and put it in the engine itself. So you're not doing compile as execution, you're compiling, pre-compiling your information. So we compile your T-SQL in the machine language, and we make a DLL out of it. So you now can do, you call a DLL as you would normally, no changes from your application standpoint. Calling a store procedure, you call now a DLL store procedure, and so these are aggressively optimized for compile time. So they're pre-compiled with statistics, so they know, so they get the answer very, very quickly back to you. So it makes your business logic processing very, very efficient. So many core processors, if you've seen the trends from Intel and other manufacturers, that we're getting more fewer sockets with more cores. So again, more processing power to the end user, which again lets us do high concurrency. So within In-Memory OLTP, we do use snapshot isolation. So we have multi-version optimized concurrent control with full access support. So basically what you're looking at is a system that will handle multiple transactions at one time without locking, without latching requirements. Because of this, you get very frictionless scale-up. So as I add more cores to the system, the In-Memory OLTP processing engine consumes it very quickly and lets you run very high concurrency operations across that. Now from the business standpoint, in total cost of ownership, it's a pretty nice package here. So you're not, rather than having to buy SQL Server 2014 and oh yeah I want in-memory and oh yeah I want in-memory OLTP and DW, I buy SQL 2014. It's all integrated together. So the manageability you're used to, the administration support and development experience are all exactly the same, whether you're running disk-based tables or in-memory OLTP tables. The queries, again, look the same, and the things like HA, high availability, Azure support, backup restore are also consistent across any experience you have there with either in-memory OLTP, disk-based tables, or DW queries. So you get a hybrid engine, in-memory OLTP engine, and an integrated experience across the entire platform. So again, the total cost of ownership is very, very low in that point, and it's again a nice, consistent platform across all pieces. Now, how does it fit together? So this is a picture that kind of shows you what SQL Server looks like today, as you all know and love. We won't go through all the pieces, but they're pretty much there. So things that are in gray are existing components. You've got data file groups with some tables out there and their logs and their indexes. You've got the buffer pools in there as well, again, tables and logs, and an execution engine for your SQL queries, a parser, and that's what you see today. The client application talks to the session manager, talks to the query executor, and those things flow through that as you know and love. So now you add in the in-memory OLTP or Hekaton in this case. So now you get a separate piece inside the same SQL Server exe that handles memory optimized tables and indexes, plus you get a memory optimized file group. So now the file group is not the same as you had before. It's a different type of file group. It's file stream based, but you do have a third basically file group or file location. So as you move the environment to in-memory, they will flow over to the in-memory portion of memory that we keep segmented out for ourselves. The tables themselves leave the data file groups and go to the memory optimized data file groups. And notice what is gone now. The transaction logs have gone, at least the index part of it, because where we keep all indexes, both hash and range, in memory. So we don't have those pieces anymore on the transaction log. But the tables themselves are still there. So we're still doing logging of your transactions through the normal transaction log process. So to migrate those tables back and forth, you don't just say, move to A from B. You basically drop the table, recreate them as an in-memory table, and then put your data into it. So you now get these tables in memory. You now have some queries that you've written in T-SQL. You can run them unchanged in a thing we call interop mode. So basically, rather than having you recompile your store procedure or change them, you run it as is written today. It can access both memory optimized tables and traditional disk-based tables in the buffer pool without any changes at all. Now there is an overhead for this one. We have to do some translation when you start talking to the memory optimized side. So there'll be some overhead for doing that. But you can again run unchanged in your current environment. But to get the true benefit from memory optimized tables, you run them what we call native mode. So they're natively compiled. So at that point, you rewrite your store procedure as a natively compiled store procedure. In most cases, it's basically just putting some decoration on the top and the bottom, and we'll look at a few seconds how to do that, that basically instructs SQL that this is a natively compiled system, and now I'll handle it differently. So it goes to a different compiler, and it's compiled into this DLL we talked about before, and that will be used, called like you normally call it from your application, as the new store procedure for that one. So there's also a concept you talked about, our transaction logs and being on the system. So you do have the ability to have a table that is persistent. So it'll be if you have a system failure, you reboot the box, we will flush all the data back to disk, and then when we come back up, we'll recover that database back into memory. So that table, in case table 2 or table 1 in this case on the picture, is always persistent in memory. So if you shut the machine down, we'll bring it back up when you reboot the machine back up, and T1 is still there at all times. There's an option also run which is called non-durable tables, and we'll see an example in a few seconds on that one. And these tables do not persist, so they're transient in nature. They're used for simple logging processes or things that may be transient for your application. data recording operations, I operations during transition processing. All data is in memory, and that's where it only is. If you have a server crash, or even an always-on failover, that data is lost. But it's very good for staging tables, web server session state tables. Again, a very high-speed, no logging, non-persistent table that you can build quickly. Now, we talked about how we get our tables from the buffer pool normal data file groups into memory optimized. So it's pretty simple. There's a normal create table DDL, so we're going to create a simple customer table, 3 columns, 1 index, actually 2 indexes. So the first thing is we decorate the create table set with a thing called memory optimized equals on. And that instructs SQL Server to note that this table goes in the memory optimized file group you created, and we'll treat it differently. This table is also durable. So because we say schema and data, that tells us SQL Server to keep both the schema, the table layout, and the data persistent. If we had said schema only, there would be a non-durable table. All we would keep around is the table structure, and all data would be lost on any kind of system failure or system shutdown. So in-memory tables use hash indexes, and to do that properly, we have to have you define a bucket count. So the bucket count is basically how many locations in memory we're going to reserve to keep your index records. So right now, the current recommendation is you take your 1 to 2 extra number of unique key values. So that's your bucket count. So in this case, we're sitting at 1 million. So we probably have maybe 500,000 unique values to that one. At this time, that number is not changeable unless you recreate the table. So it's set once, and you're basically locked into it until you recreate the table. We also have on the same table with our non-clustered hash index, which is our primary key, we also can create non-clustered indexes as well in the system. So now I have an index on customer since that's non-clustered, and both are available to my both natively compiled and interop queries can both access those indexes and use them. So now we're creating a table. So we've got our normal table, and then we create table type. So if you're using the table variable parameters where you're going to pass in large chunks of data into a table, into a TVP, and then use that in your stored procedure, exact same process. You create a table type versus a create table. You can specify indexes, the same columns, and you also say that, that memory optimizes on. That says create this table space, this table variable in memory, not on this base. So to create a procedure, so you've got your traditional T-SQL you have today that runs just fine. You know and love that one. But now I want to be able to create an in-memory or a natively compiled stored procedure. So this will create a DDL for the, in this case, insert order stored procedure. So the key things to add to it. So first of all, you'd say native compilation. So again, that instructs SQL Server that this will be a natively compiled stored procedure. It will compile when you create the procedure, and then use that for all subsequent calls to it. We must bound it to the schema because the schema could be non-persistent, so that must be bound to it. We keep that kept in line with the stored procedure itself, and we have to give it an execution context as well. So every natively compiled stored procedure must be in atomic blocks. So if there is not a transaction out there, it'll create one for you. Otherwise, it uses save points. So it's a pretty simple concept, but it has to be decorated with that one. And finally, you tell us what the session settings are for that one, which is, in this case, snapshot isolation level, and the language using is US English. Now, the next piece is the deceased T-SQL. So everything else you'd normally do before will fit underneath that with transaction isolation level blocks. So now you've got your same stored procedure before. You've now decorated with these create procedures that do natively compilation. When you create the procedure, you'll get a DLL in memory, and then I will call it, in this case, my application will call insert order as it did before the interop mode. The exact same behavior would happen from the application standpoint, though much quicker. So with all of these features, there still is a lot of durability and availability happening in the background. Some are automatic for you, and some are supporting other features that are out there. So every operation is logged in the database transaction log, period. So So you get full durability as your default. But you can, if you like, modify that some to use delayed durability, so don't do my log writes until later, or I can use non-durable tables. Those are the tables that do not persist with the system shutdown. So in that case, I'm not doing any kind of transaction logging. You've also got new types of data files that are out there. So we have append-only data and delta files. So similar to some of the columns or indexes where you have a file that we're just going to add to, and then one of the changes of those files, we do the exact same here, and that uses file stream the coverage. So again, a very high speed access to those files again to make sure that we're not blocking down those high throughput transactions you're running. Because it's integrated as part of SQL Server, you still get the full backup and restore support and full backup and restore experience you get with the current disk-based tables with in-memory tables. I can back up a memory optimized file group with the exact same command structure, and I can both do full, differential, and log backups of those same structures, again, unless I'm running durable tables, or not, sorry, non-durable tables. So again, the experience is exact same whether you're doing disk-based tables or the in-memory OLTP tables. We also support failover clustering. So in an HA environment, always-on environment, if you have a failover cluster defined, then you can persist those tables, those in-memory tables, across that failover link. The only issue is that there is one small timing lag where if you do have a failover, we have to then bring the data from the persistent durable table in memory and load it in the memory. So there is some time lag there, and that could be a minute or two based on how much data you have in that table. If they're incredibly large, you will see some time lag there. But the key thing is that you can get that same failover experience even within memory tables. So we also support always on, so our HA packaging. We do both synchronous and asynchronous secondaries, and they're also readable. So a memory optimized table on a primary system in always on has a secondary sitting out there, or multiple secondaries, and they are readable. So I can get access from multiple situations or multiple systems very quickly. Now, when you move from interop queries to natively compiled queries, there are a few things that are not supported in SQL 2014 right now. So on the table side, we don't support triggers, so no DDL, DML triggers. There are ways that have been documented. There's blog postings on the web about that, about how to get around that one. You can create a wrapper store procedure in traditional T-SQL that does your triggering and then calls the compile store procedure. So you can wrap those things around that with different functions. On the data type side, we don't support LOBs, no XML, and no CLR data types in memory tables. There are also no foreign key or check constraints. So like we did though with the triggers, you can again write a wrapper around it very simply to do the foreign key checking for you outside of the in-memory natively compiled store procedure, call that store procedure to do the actual in-memory operations and come back out. So that gets you away from some of the overhead you might have for trying to run everything through interop, because there is an overhead, a price to pay for that one. So you can't change your schema once it's defined. So there's no alter table for in-memory tables. So you can't alter a table and add a column, change a data type, change the table itself. You have to drop the table, recreate it, and then reload your data back into it. There's also no in-memory index. So once you have an index on a table or your bucket counts are set, you cannot change those as well. You must, again, drop, recreate the table to get that change for you. On the natively compiled side, in the store procedure itself, there are also limitations there as well. You can't do outer joins, distinct, no OR, no subqueries, and no case statements. Again, to get around some of that stuff, people are writing wrapper functions around the natively compiled because the core function, the C they want to get to, runs very well natively compiled, but they'd have some decoration around that to support ORs or distincts or case statements. It's also limited built-in functions, so the core math, date, time, string functions are supported, but the other functions are not there. I will be honest, this has been a big block over some widespread adoption right now, but we're learning as we go along on how to write these wrapper circuits around things and make sure it works better, and we're also getting more knowledge on how we can do different things inside with the natively compiled limitations. So perfect results. So this is where it usually boils down to. We spent a lot of time in the early days of SQL 2014 working with a large set of customers and helping them from the development side, helping them get through the migration to In-Memory OLTP to one, do a proof point for us to make sure we're in the right direction, and two, to see what we can really do application-wise and perf-wise for them. The first one was EdgeNet we worked with. They provided retail and product delivery for end consumers. They had a system that wanted to be a real-time insight into the product priceability for retailers. So basically, they wanted real-time data coming back from the system, and it was a pretty widespread, worldwide system used by retailers and stores and consumers. So we did the initial conversion from their disk-based tables into in-memory, and this started converting as many of the store processes we could to make sure they were natively compiled. So we got, based on where it was, 8 to 11x performance gains. This is for the ingestion piece of it. So as data is coming into the system at the high rate of speed, the previous system, all disk-based tables, occasionally had trouble handling the incoming workload. So with In-Memory OLTP sitting out there, we got at least an 8x in some cases based on the transaction size and data size, up to 11x of perf gains on getting data into the system. I'm going to take a little silent here for a second. There's one nice thing about In-Memory OLTP that we talked about quite a bit is it acts as a shock absorber. So a lot of places have data that is pretty consistently coming in at a nice steady rate. And that's pretty easy to predict for. The problem is when you get these spikes of data that may overwhelm your system. The In-Memory OLTP engine can handle the ingestion of data very well. So it can actually, as you increase the number of requests coming in to pump data into the box, it will handle that very quickly and return control back to the calling application. We've seen a lot of cases where people are seeing the 25x numbers of being able to get data into the system they couldn't do before because the shock absorber system works very well. It's just that it happens, and then you just sit differently for it. You just basically say, here's my memory OLTP table, write data to it. As the loads increase, it will increase the throughput. It's a very nice system to have, that one. So back to EdgeNet. So they were able to take their multi-server, multi-tenant system, which is a pretty large system, and scrunch it down to a single database server for this one. So the TCO, and this was a pretty high end for them. The perf gains were great, but actually they were more impressed by the ability to squeeze the thing down to a single database and server box, help management, help hardware costs. Plus they were able to also take out a caching layer from the client tier because the previous system was getting overwhelmed by the requests coming through. They actually put a caching which added latency to their clients, and that in turn gave them a low perception they needed to get that out of there. So this took that piece out and allowed them to basically run 8 to 11x faster on a single box without this caching and artificial latency. Actually, our first big win was bwin Party. So they're a European online gaming site, and they had some of the classic scenarios. They're using ASP session state, which is very high-speed transactions and non-persistent. So if you're logged onto the system, you're doing something, and you just basically quit, they don't want to keep that information around. They don't care. They also had the traditional shock absorber environment. So as a sporting case of the World Cup going today, they would see a massive spike in people placing bets on the games. So that would be a very high spike they could have to plan for. But traditionally, the rest of the time they were there, it was a much lower rate. So they had these massive spikes they had to handle. They also had a real problem with end-user performance. So their money is made by giving the customer a good experience when they place their shopping cart of bets. They want high-speed access to that one, and they also want a high-speed return back to the end user saying, yes, your bet was placed, we're good to go. So we did a lot of work with them in the labs here in Redmond to basically convert their entire application over to In-Memory OLTP. So before they did the transition, they're running basically 15,000 batch requests per second, so 15,000 transactions per second. We did a control study in the lab. Here we got over 250,000 batch requests. Exact same application on the front end, but OLTP, In-Memory OLTP on the back end. We actually were able to pump it even higher to 450,000 in some lab testing that was a little artificial, but again, it showed the promise was there. So today they went from 18 SQL servers trying to handle the load down to one box doing the exact same load, actually doing more load than before, able to handle those peaks of high-end gambling or the spikes of gambling bets being placed very quickly. So now this is all based on the non-durable tables. Again, because, well, I take that back. Part of it was based on non-durable tables because if you're running your shopping cart, if you were to not place those bets and just to board out and leave, they didn't want to keep that information around. So that shopping cart stays around until either you get out, log off the system, or you place your bet, and at that point it's preserved in durable tables. That was a record of where you came from. And the last one we worked with really closely, there was a bunch more, but these are the three main ones, was a Japanese foreign currency exchange platform. So they're basically trading currency, high volume and very low latency. They needed a pretty big, they were expecting a 10x volume increase in the amount of trading they were doing. So as global economies become more and more integrated together, there's a lot more trading back and forth of currency. So we did some work here with them again. We got basically 2x throughput with 3x in the labs, but 2x in real life. Latency went from 4 seconds to 1 second per transaction. So they were incredibly happy with that one. We've also rolled out to a bunch of internal customers. Our Microsoft.com website, they do all their log management, security management through Hekaton and memory tables where they can pump in billions and billions of rows every hour, do some massaging of the data, and then pump it out to a DWS system later on. So again, it gives them the ability to handle those high volume throughput systems. So these are your mileage may vary numbers, but we'll throw them out there for you. So the best fit applications, so what can you expect? So 25x, that's a pretty high number, but if you have the full advantage of the system, and I would say it's a very narrow case, but like web app session state systems where you don't have durable tables, you can be non-persistent, you're very high speed or low latency, high number of transactions, and high small transactions, you see 25x. With systems that ingest lots of data coming in, that shock absorber approach, and heavy read, you'll see 10x. Again, your mileage may vary on these things, but basically you want lots of data coming in, either predictably or with spikes of input, and then heavy random reads on that one. So legacy apps, I've got an application, I'm not going to change much on it. Based on how the app works, you'll see 4 to 7% or 4 to 7x per improvement on those things. Again, your mileage may vary on that as well based on the application. We've even taken a workload derived from TPCC, so it's not a full-blown TPCC workload, but it's very similar. We've been working on it for, it's 20 years old now. We've been working on it internally for a long time. It's very highly tuned and highly tweaked. We can still get about 2x on that same workload, just taking it, converting it straight over to In-Memory OLTP. That's both in interrupt mode and in natively compile mode. So the promise is there. It just depends on the application and how it characterizes them and fits the pieces of In-Memory OLTP. Just for some more proof points, we did a couple of micro benchmarks, so basically in-house written things, very simplistic. We did this one's a lookup table, so we did a random lookup in a table of 10 million rows. All the data in memory was regular or memory optimized, so there's basically, the regular stuff is disk-based tables or native SQL, other pieces of memory optimized. It's a basic Intel box, and basically we're looking at about 2.7 million lookups per second per core on that system. I won't go through all the numbers there, but you can see, look at 1,000 lookups. We basically were to do an 18.9x speed up between regular disk-based tables and memory optimized tables. Again, this is a benchmark. I'm from the benchmarking world, and benchmarks are basically lies packaged with a nice bow on it, but you can kind of see the promise is there for it. Now, when you start looking at updates, you also do the same thing, same application. Now we're doing random updates of 10 million rows with one index and statualization. Now, because we're doing that many updates, we took the log out of the picture. We disabled log I/O because it was becoming a bottleneck. It wasn't really helping the benchmark, the test as well. So we got now about 1.9 million updates per second per core, which is pretty impressive. We use our same number of 1,000 transaction size, that number of lookups. We basically did a 27.9x improvement, speed up the number of cycles used to get that information in. So again, the promise is there. It may take a little bit of application changes to make that happen, but it's a very good platform to start building these things on. Now, key takeaways. What comes of this thing? Well, we saw actually a while back that we needed to have some changes to database systems because there were things happening in the architecture from both hardware and software that we need to take advantage of. There were increasing demands for low latency and high throughput. And we were painfully aware that the traditional disk-based tables were becoming a bottleneck for these low latency, high throughput expectations. There are also a lot of hardware trends, and the biggest one is the declining price of memory and the more cores per socket. Those are the two biggest kickers that push this thing. So to take advantage of those, we need to think something different, and that was In-Memory OLTP or Hekaton. So you can take advantage incrementally. We're talking about doing interop mode, so I can drop in my In-Memory OLTP, I can put my tables on there, run my store procedures unchanged, and start my migration at that point. We also provide a really nice tool called the AMR tool, which is Advise, Migrate, Report. You run it against your production system or even your test system so you can get a feel for your data access. It will look at the transactions happening, so you run it for a period of time, and it comes up with recommendations for you. And it says, okay, well, based on your workload patterns, these X number of tables would benefit from going to in-memory. These store procedures would benefit from being, from being natively compiled. 1 second. And here's the amount of work it would take to make those things happen to make them natively compiled. It also highlights things that you could not do. For example, if you had queries that had lots of distinct joins in them, it would highlight that, well, you get a lot of advantage from that query being moved to natively compiled, but we don't support distinct joins. So it goes through and tries to help you get through the process of migrating your application SQL code and tables into In-Memory OLTP. And I believe there's a session later today on the AMR tool from George Lee. So if you have time for that one, I definitely recommend watching that one. Again, use those memory optimized tables in a migration mode without changing out your store procedures of the day. And as you can, natively compile the store procedures, move them over. The application remains unchanged, but you do get the ability to start moving your environment to an In-Memory OLTP and get some of the gains. Again, performance gains 2 to 25x. Your mileage will vary on those things. There are many differences that will happen, but it's a great way to bring the low latency, high throughput environment into your system with in-memory technology. With that, I think I am done, so we'll open it up for questions.
Thank you. The first question is, if data volumes change, do I need to recompile the native store procedures?
So the first part of that question I didn't hear?
If data volumes change, do I need to recompile the native store procedures?
No, you do not. Only if you change significant things like I added an index, and I make sure I use the index, or I added columns, but anything that changed underneath as far as a data volume, it doesn't matter.
Okay, thank you. As in-memory store procedures are compiled as a DLL, does that mean they use memory assigned to the OS, or do we need to reduce the max server memory for SQL Server?
No, we keep them in the same In-Memory OLTP engine that data is stored in, so it's basically co-located.
Okay. And then how is an in-memory object different from the DBCC pin table?
So in a pin table, we basically reserve part of the normal buffer cache, and it was a kind of a limited function, so you could access it with normal store procedures. If you think about interop mode, if I'm running interop mode, it behaves very similar as pin table, but you don't have the locking and latching overhead you'd have for pin table. So pin table is basically behaves as a normal table with locks and latches happening, but that table never gets flushed out to disk. The In-Memory OLTP table, there's no locking, no latching, never gets flushed, and you also can do natively compiled store procedures. You will get more throughput from the in-memory table than a pin table. But it was a nice migration point across.
Okay. The next question is, while creating a memory resident table, what if I don't give the option durability equals schema and data?
So you have to give it an option, either one, so either schema and data or schema only. So the schema and data says to persist, so it will, all the transactions are logged, the indexes are all in memory, and the table itself is protected as far as if you reboot the system, data is pushed back into recovery time as you bring the SQL Server back up. If you don't specify that, you'll get schema only, which says keep my schema, my table layout, but if I stop and restart SQL Server, the data in that table is now gone. Nothing was kept there. But you're forced to put one or the other, or you won't be able to build the table at all.
And can I restore a database backup from an in-memory server and restore it to another SQL Server?
Yes, as long as they're both SQL 2014 and both using in-memory technology. So I can back up an in-memory database on server A, restore it on server B. And
is this feature available in standard or just enterprise?
It's available in both editions, though there are some limitations in standard. I don't have them in front of me right now, but there are some limitations there.
And are there any limits for database sizes or object sizes?
So, let me get a drink of water quick. There are some limitations that are theoretical. So today, an in-memory OLTP database can be about 255 gigabytes in size. That's the maximum size. If you go up to that level, you'll start getting out-of-memory errors, and you won't be able to add any more data to it. It'll still be readable, but you can't add more data to it. So that's the current limitation today is 256. And that's really based on not on the memory size or anything else in there. It's basically how we did the files to keep track of the non-durable, to keep track of the durable tables. You had to have checkpoint files sitting out there in the file stream, and the limitations of how we did it in the past. It was based on how we did disk-based tables, which there was a number of certain size files that were created. We kept that same structure for in-memory, just made it file stream as a kind of a jump start to get the thing going quicker. So today the current limitation for durable tables is about 255 gigabytes, and non-durable much higher than that one. We haven't seen a limitation on that one yet, memory size at that point. Okay. It's all based on the checkpoint files, not the actual physical size of memory.
And can you compress the indexes as you do in the file objects?
Not today, no, because they're not hash indexes, so they behave very differently. So they're not compressed like you would in a normal disk-based system or in a cluster column store, but they are. Let's leave it at that. That's where they are today. Yeah.
And how do statistics affect the compile processes of natively compiled stored procedures?
Yeah, and actually there's quite a bit. So before a normal process of building an in-memory database is you would create your table space, load your data, create stats across all those tables, and then create your stored procedures on top of that one. That ensures that the native compile store procedure gets the most accurate information as far as the hash bucket counts and everything else, so we get a nice orderly layout of the data in the hash buckets, and you get high-speed access. If you don't do it in that order, you may or may not see a difference. It depends on the data at that point. Anywhere from, well, I noticed that to, I did it differently, it didn't make any difference, things are good.
And do memory tables get fragmented? And if so, how do you defrag them or rebuild them?
They don't get fragmented, so it's not an issue at that point. So the only issue you may have occasionally, and we've seen it with systems that are very high throughput systems where you get a lot of data churn, that the hash indexes will get a little bit cluttered, and there are utilities to go out and clean those things up. But we find the best way and fast way to do it is just to basically drop the table, recreate it, change your hash bucket counts, and then come back in with new data.
And is the in-memory OLTP going to be supported in SQL Azure?
Yes, that is coming soon.
And any idea when foreign keys will be supported on the in-memory tables?
So we're doing our planning for the next releases of SQL Server, and that's high on our list of things to do. I don't have any dates or anything yet, but it is coming with the headlights on bright. So actually, the whole surface area is going to be, it's our main focus areas now, is to expand that to remove any kind of any blockers for adoption.
And there's a couple questions out here about what happens to the data for a memory crash, if you could talk about that for a second.
So it all depends. So if you're running a durable table and you get a system crash, then it'll recover like you would normally recover a disk-based table. So you would have recovery process walking the transaction log to replay those transactions back in. You could also do a restore from a backup, back up your log, restore from backup, and then replay your transaction that way. Is well, that works. If it's non-durable tables, that data is now gone. So you lost everything at that point on a crash. That's why they're what's an edge case, but they're highly specialized on where you use a non-durable table. There are things that are transient or could be recreated pretty easily if something did fall apart. So those are, again, not an edge case, but very focused on where you use a non-durable table.
Okay. And why are there no clustered index support for the memory optimized objects?
That was a design decision. We did have, this has been in development for quite a while internally, and we had a point where we need to either ship it or kill it, and so that was one of the things that didn't make the first list of functions for the product. So rest assured, it's on our list of things to keep looking at. So there's quite a big roadmap for moving in-memory OLTP beyond where it is today.
What is the memory requirement for turning this feature or using this feature within an OLTP environment?
So basically, there really isn't one. So if you have a 2 gig system, you try and build a massive table out there, you're going to have an issue at that point. But we recommend 16 or more gigabytes of storage because that just gives a nice place to play. But anything beyond that is even better. So if you're trying to approach that limitation, or not limitation, but the ceiling of 255 gigabytes, then you want a system that has enough space for both your OLTP tables in memory and your disk space tables. Because remember, we're fighting for space with normal disk space stuff. So you may have existing applications that they're running on disk space tables. They have buffer cache. They're using their normal buffer pool, and you try and jam in memory tables in a small memory system. You may have issues with someone's going to get starved out, and in this case, the in-memory OLTP doesn't play with others. We'll take over the memory, and that's actually blocked and locked for us now. Buffer pool will decrease, and you could see performance issues with your normal traditional disk-based table environment. So the recommendation is, see where you stand today, make sure to remember in the box, and run the AMR tools to help you get around some of those issues and make sure you're not overloading the system and trying to collide too many in-memory things with things that are normal traditional disk-based and buffer pool.
Okay. And then how does it affect a clustered system?
So currently today, we don't support Hekaton in a clustered environment. In-memory OLTP is not a clusterable. It's clustered in the context of failover support or HA where you have readable secondaries, but it's not a true cluster system.
Okay. And one of the people had noted that the documentation says it's supported in the Enterprise Edition only. When would the standard edition be available?
I don't have a date on that one yet, but I can actually, if you send that question to me, we can post it on our blog posting.
Okay. And do I need to recompile the statistics where I have a lot of inserts and updates?
So what we found is a good rule of thumb, and it's one of those rule of thumbs that you can apply based on your environment, is if you are a highly churning environment, lots of inserts, updates, because an update is basically a delete and an insert. We don't do in-place updates. That we found it's good to, and I'll use a term, but it's not really true, but reorganize your indexes after a while. So we found it's best to, and we see this actually in real practice at our ms.com site, is where we will, once every 2 weeks, off hours, drop the tables, recreate them with a different bucket count because things are growing, and we load our data back into it. It's not a very long process. We're probably looking at maybe 15, 20 minutes for their multi-million row tables, but we found it kind of helps keep the system nice and stable through the entire processing window of several months. So it's a yes or no answer. If there's a lot of churn and burn on that stuff, you may need to do that regularly, but right now it's not an issue in most cases, but just in some certain edge cases.
Okay. And there's a couple questions out here about when would you want to use a non-durable memory table?
Yeah, once it's an edge case, but it's very specialized. And the recommendation, the example we normally use is for our bwin environment, they have these session states. As you log into the bwin system, almost like your Amazon shopping cart. So you have this thing out there that's transient in nature. So I'm going to start making some either gosh, I want to buy paper towels and this from Amazon. So as I'm doing that, I'm building this little table up in memory of these things I want to order. At that point, I may do a couple things. I could say, well, I'm kind of done, and just abort out of that thing and kill my cart and move on. So at that point, the vendor B1 or whoever doesn't really care about what that information was. You said you didn't really want to do it, you aborted it, and you went away. The next piece would be, I've got, if I had that same table in memory, so now I'm making my bets, for example, and I say, okay, submit, place, commit these bets. At that point, it moves from the non-durable table to a durable environment because I want to keep that record of your transaction, and then it goes away. So it's basically things that you don't really care if the data goes away or not, because either it can be recreated from something else, in user or memory or data from a different table somewhere else, or it's things that are very transient. Think of like a temporary table almost that you would use for a scratch pad or something and then get rid of later on. So it's kind of specialized, but the advantage is it's very high speed, actually higher speed than a normal in-memory table, because there's no logging overhead for all the changes you're throwing in there. But again, it is something you would lose.
Okay. And since we can only create non-clustered indexes in memory, what would be the impact of having and not having clustered indexes?
Well, yeah, so if you think about a traditional disk-based environment, the big benefit is that your data is co-located with your index. So it's basically the data is the index, vice versa. That's because you're doing a bunch of locking and latching to get that data back, and in high concurrency systems, that can become a big overhead. That doesn't apply in the memory tables anymore because there's no locking and latching at all. It's all snapshot based, and so we can get the data very quickly. So the actual benefit of clustered indexes in that environment doesn't really apply to in-memory OLTP as well. So it's not a big deal really right now. We have heard the requests for it, and the discussions have been around, but we haven't. It's the environment is so different that it may not apply the same way you traditionally think it would, whereas a hash index or the non-clustered perform just as well, if not better.
Okay. And can you explain the drop table and reload table from a native table?
So drop reload from native table.
So, as you mentioned, rebuilding these objects if you had a schema change or basically clearing it out. So how do you get the data back into the table, back into the memory?
Yeah, so the process today would be to export your data out to some file. The best way is just using like SSIS or those tools to export the data back out into a flat file. Then you do a normal drop table command like you normally do in T-SQL. Nothing changes there. Modify your table create script to be, is it different columns, is it different data types, whatever it is, different bucket counts. Recreate the table, load your data back in SSIS or import or whatever you're going to do at that point, and then run your stats, and then create your store procedures again. At that point, you've got the new table layout. We have new stats on it. Everybody knows about it from the store procedure standpoint, and you should be back good to go. It's definitely a mechanical process.
And there's a high-level generic question about there's a customer not facing any transaction processing issues. Clients are happy, but when should they use in-memory, and should they?
Well, that's a good question. That's where the AMR tool comes into real benefit here. You can run it. It sits in the background and watches your current application happening and access patterns, your hot tables, what store procedure running more and more. And it'll give you a nice snapshot of what, if anything, and in case maybe nothing in this environment, where in-memory OLTP would help you quite a bit. It gives you both the, gosh, if you can move this table to in-memory, it would give you a benefit, or this table won't help you at all because of its size or whatever else is, or access patterns. So it gives you a nice way to go through and figure out, one, will this help me at all? And then two, if it will help me, is it possible now? How hard is it to make that transition over to in-memory OLTP versus traditional disk space? So again, the AMR tool is our ace card to play on that one to figure out, does this make sense? And in our testing early on, we were doing this before we released the product. Some internal applications ran the AMR tool against, and they said, it might help a little bit, not much, but a pretty heavy migration penalty for what you've got based on your environment. So we basically aborted on the process. It didn't make sense for them. So it tries to help you not go down a path that you may not need to go down. That's my AMR commercial for the day. So.
And does this work with ad hoc SQL, or does everything have to be pre-compiled?
So ad hoc will work. So like but in interop mode. So you may, if you were to run that same query, a million times, ad hoc or native stored procedure, you might see a slight benefit in going with the natively compiled, but ad hoc works just as well in interop mode. So.
Okay. And how much memory would be needed for a 1 million record table?
It's hard to say. It depends on how wide the table is, how deep. A million rows, is it one character? It's pretty much. There used to be some formulas on the web, but I had to look it up again in our blog posting. But there are some formulas out there to help you kind of calculate that one. But it's based on column type, density, and then your hash bucket count. I can't give you a real number on that one right now.
And that's all the questions we have. We want to thank everybody for their time today, and thanks for the great presentation.
All right, thanks everyone.